the correlation in time. So there I can say I have u prime at x, y, z at time t, and let us say I am looking into u prime itself at x, y, z, t plus delta t. Delta t is the some time interval separation. So I am, let us say the first signal started at time t equal to 0, I am checking every milliseconds, okay, 2 milliseconds, 3 milliseconds and so on, till I see that after some time it is not correlated anymore. So I can take a sample. So I collect all this data to do statistics, okay. So I can do this now, average over this, and you can normalize this if you want. This is correlation in time. If you want to get the correlation coefficient, then you use the reference data at time t, okay. This is at time t, this is a t plus delta t here after certain time interval, okay. Delta t is the time interval.
So this averaging is in time, it's time averaging.
This is, yes.
The previous
We are generally working with ensemble average here. So in practice only, as I said, you can do that. You can do, I mean, many of these things we do it in as an arithmetic mean. So over bar in the course represents it is ensemble mean whenever I use it.
ensemble mean, I missed the last class, so it's still like ensemble mean can be done in time as well, right? Like it just
Ensemble mean is always a function of 3-dimensional space and time. It's not time average, okay. Yes. So if you want a correlation coefficient, then you take the reference as at t, and delta t keeps changing, but the reference is t, so you can do a correlation coefficient like this. So the coefficient, correlation coefficient is u prime of x, y, z, t, u prime of x, y, z, t plus delta t over u prime of x, y, z, t, you take the square and then average to get a correlation coefficient in time, or the temporal coefficient, or an autocorrelation. Now there is also, this question has come now, okay, this is like a vortex or an eddy is coming in, and I am waiting for after a certain time, so that I know that this has passed over it, and so that I can collect another sample. That is fine. Now sometimes you are interested to know spatially how large a turbulent structure is sitting, its spatial dimensions of a turbulent eddy. For that one can do what is called a 2-point correlation or a multi-point correlation, okay. We have looked into only single point statistics, we can do multi-point statistics, multi-point statistics. In this, one interesting component is 2-point correlation. This is to see how large this eddy is. I mean, you cannot see everything using your naked eye, okay. You need to quantify it. You cannot approximately say this is like looking like 10 millimeter, right. I need to exactly quantify the size of a turbulent eddy in 3 dimensions, its length in x, y, z. Then you can do this 2-point correlation, which is basically, then I can look at the u prime of, let us say, the 2-point correlation in x direction, then it is x, y, z, t, u prime of x plus delta x. So delta x is the spatial interval that I am giving, y, z, t. This will give me this information gives me like what is the spatial extent of a turbulent eddy in x direction. So I can say that okay, this will be useful. For example, when you simulate it, you need to have these eddies sitting inside your computational box, right? So if your box, let's say the length in x direction is let's say 1 meter, but the turbulent eddy is 10 meters the size, then obviously you are not simulating it right, right? So your box has to be bigger than the turbulent eddy, the largest turbulent eddy you have, and therefore 2-point correlation helps in finding out how large computational domain you should have. Okay, so this is useful, this multi-point statistics. So the statistical part I'll stop here, I'll not go into much more in depth. This is sufficient to know basically how to split the raw signal or the instantaneous data into a statistical component and the random component. Now engineers are interested in the statistical value, but you need the information of the randomness to compute the statistical part, and physicists are interested to learn turbulence, so they are interested in the random component. Okay, so now we know how to split. If you have the data, I know how to split, but the application of this now is we will use it in the governing equations. We want to split the terms inside the governing equation, the statistical component and the random component. So we go towards that part.
Multi-point statistics, like in 2-point correlation analysis, do we take the RMS like in division, or like?
This multi-point statistics is, as I said, it could be u prime and v prime, but you need to know why you want to do that, right? The question, you need to ask the question which component I am using and which interval I am taking. It could be a general correlation where you are looking into u prime and v prime correlation, and it could be x plus delta x, y plus delta y, z plus delta z, t plus delta t. If you want to do that, go ahead and do it. You need to ask the question, why do I need this? Now I want to study the correlation in each direction first, in x, y, z separately, so that I know its length. Okay, fine. So with this, now we have to proceed to what is called the governing equations part, but before that, all this we have done here is we need to apply the statistical analysis part into the governing equation. So the objective is to apply what we learned in the statistical analysis to the governing equation. To the governing equations, to see what does the equations tell us, right? Just by doing this decomposition, the equations can tell a lot of information. So that is the objective here, to apply the statistical analysis to the governing equation, so that we can get an equation for the mean fluid motion, an equation for the random fluid motion separately. Okay, and then we see how to model them. All right. So before that, how many of you are familiar with Cartesian tensors? At least those who have taken CFD course will be okay. Not everybody. So let's quickly do this so that everybody is on the same page. We need Cartesian tensors throughout this course. Equations get very complicated once you start to decompose the governing equations into statistical and random component. Okay, so we'll quickly review what is called Cartesian tensors. Cartesian tensor notations. I will not go into the depth of the entire this tensor calculus. We will only look into the extreme basics, what is required to write equations and decompose them. All right. So for that part, so Cartesian tensor notations are useful to write equations in a compact way. So you can write equations in a compact way, in a compact fashion. okay, and it will also help with ease of programming. It's based on indices, which means ease of programming, as against using vector notations, okay, and it's also easy to represent high ranked matrices. So easy to represent or write high rank matrices. So those who are familiar would know this, otherwise it's not a problem. We'll quickly get into the basics. So in the vector notation, this I believe everybody will be familiar with. You would write, let's say, velocity vector like this, u with a arrow on top. This basically implies you are looking into the three velocity components here, u, v, w. In Cartesian tensor notation, we use an index, as I already said. This is based on indices, okay. So we write this as simply ui. So this will be u1 comma u2 comma u3. It will go into an indexed based notation here, and there is something called rank of a tensor. Rank of a tensor. So for this we can say, let's say this is the rank. Let's say we have a 0th rank. So a 0th rank tensor is basically a scalar, okay. So the name for this is a scalar, and the notation, let's say I am using it as some scalar quantity b, and number of components is basically 3 raised to n. N is 0 here, so this is the rank. So this is basically a single component, it's a scalar, okay. So an example could be your temperature, pressure, and so on. So then we have a first rank tensor, which is a vector. Instead of this arrow mark, we write, as I said, indice. We use an index bi. So I can take value 1 or 2 or 3, b1, b2, b3. So number of components is 3, okay. So example is your velocity vector, right? Velocity vector. Then you can get a second ranked tensor, which is called tensor only. This some of you have done even in quantum mechanics would know this. People use in solid mechanics also. They use the term tensor. So I represent this as bij, because this will give 9 components here, a tensor. So this is 3 raised to, so I get 9 components. For example, your shear stress, tau ij, and then you have a third ranked tensor. This we will encounter in the turbulence class. So we have this also called tensor. There is no special name for it. Let's say I call bij k. This will give 27 components, okay. So there are some special tensors. I will see what, for example, there is something called a Levis-Civitas tensor that we will use in the course, epsilon ijk. Okay, so now we will simply look at the components, corresponding components of Cartesian terms with respect to the vector equivalents, okay. So before that, let's see, there are three rules of tensors, three simple rules. One is called a free index rule. So what this essentially a free index rule means that if I take an example, it will be much more clear. So let's say I take an example as AI plus SBI equal to 0. So now when an index I occurs here, if I in the first term is taking a value, if I takes 1 here, then in the second one also it should take the same term. Okay. So the index occurring only once is valid for the values 1, 2 or 3. Okay. So this will be for I equal to 1, I is a free index here, so this becomes A1 plus S is scalar B1 equal to 0. It cannot be 1 here and 2 there, and you can write this as, since it is a free index, you can change it into Aj plus SBJ equal to 0 or K or anything, but you have to, if you are replacing the index, a free index, it has to be consistent throughout. This will give the same thing, j equal to 1 will give me the same answer. Okay, j equal to 1 will give me the same thing, A1 plus S B1 equal to 0. So this is a free index, we need to, if it comes, be careful that it can take value 1, 2 or 3. And the most important one that we keep on using is called an Einstein summation rule. Einstein summation rule. So this means that if indices are occurring twice in the same term, we have to sum it up. Okay, if an index occurs twice, sum over this. Index occurs twice in the same term. Okay, it's important. In the same term, sum over it. I'll give an example. Let's take an example of, let's say, AI BI equal to 0. What this means is I is repeated twice, so it has to be summed over. So this means A1 B1 plus A2 B2 plus A3 B3 equal to 0, summing over all the three components. So obviously you see that the summation rule reduces the rank. So AI is a vector, BI is a vector, but since they occur together in the same term, by summing up it has become scalar. Okay, so this has become a scalar here. So the summation rule reduces the rank of a tensor. And there is something called a maximum rule. So this essentially implies that an index cannot occur more than twice in the same term. An index cannot occur more than twice in the same term. For example, this AI, BI, CI, this is not allowed. Okay, not allowed. Index cannot repeat more than twice, and if it repeats twice, you know, you have to do the summation rule, just sum it over. These three are the simple rules that we need to know, and then we look at two special tensors that we will use in the turbulence equations. Special tensors. One is called a Kronecker delta. So it's delta ij. It's also called an identity tensor, also called identity tensor. So delta ij can take values 1 or 0. You can take value 1 when I equal to j, take 0 when I not equal to j. Okay, and then there is another tensor that we use. Another special tensor is this Levis-Civitas tensor. It's a third ranked tensor. So this is epsilon I j k. So this can take value 1, 0 or minus 1. It can take value 1 when I j k values are in successively progressive. That means it's for values, let's say 1, 2, 3, 2, 3, 1 and 3, 1, 2, cyclically varying. It can take 0 for anything other than the 1 and minus 1. So minus 1 is, it will go in the anticyclic route. So it can take like 3, 2, 1, 2, 1, 3, 1, 3, 2, 0 otherwise. Okay, cyclic, anticyclic. This is cyclic occurrence. This is anticyclic. Okay, so we have learned some tensor rules, some special tensors. Now we go on seeing how do we represent the terms that is in the Navier-Stokes equations using tensor notations. Okay, so if I take one of the term is a pressure gradient term. Okay, so certain examples. The first one is, let's say, the gradient of a scalar field. Of a scalar. So this in vector notations, let's say it's represented as, if you are looking into the scalar quantity as pressure, this is nabla p. People use this as pressure gradient term. This is represented as your dou p by dou xi. So gradient of a scalar, p scalar, but by performing a gradient operation, it has become scalar or vector. It's a vector now, right? So this is p scalar here. Your p is scalar. Let's say pressure. Okay, but this has become now a vector. This is a vector now because it has 3 terms. So we have dou p. We're looking into pressure gradient along x1 direction, pressure gradient along x2 direction, pressure gradient along x3 direction. So it has become a vector. So gradient operation increases the rank of a tensor. And in contrast to this, there is something called divergence operation. The divergence reduces the rank. Okay, so divergence of a vector field. Again, this term is very familiar. If I write it, you will know what it is. Nabla dot velocity vector u. You would have seen this in fluid mechanics, right? The divergence of a vector field. So how does this represent? We represent this simply as dou ui by dou xi. This is your essentially a continuity equation, nabla dot u, right? So when index is repeated, I is repeated twice, what you should do? It's a sum over it, right? I is repeated, so this will become dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3. So this has become a scalar here. Okay, so divergence reduces the rank. These things you don't have to remember, which is increasing the rank, which is reducing the rank. The most important part is to write the equations in tensor notations, right? Like dou p by dou xi is your pressure gradient term, dou ui by dou xi equal to 0 is your continuity equation or conservation of mass in incompressible flow. Okay. Similarly, we can have rotation of a vector field. This also has a very special meaning. People call it, let's say, curl of a vector or so on. So what is this? Is there a physical meaning to this? Vorticity, right? So this has a special meaning called vorticity. So this one is, we write this here, we make use of what is called the third rank Lewis-Civitas epsilon. So when vorticity equation is written like this, and when you want to compute, you get two differential operators for the velocity, plus there is a sign component, plus minus. Usually you mess up, you have to remember, but you don't have to remember if you are going to write it in tensor notations. So I simply write this as epsilon I j k, okay, dou uk by dou xj. Now you see this k and j are repeated index, k comma j are repeated twice. So we need to do summation twice, summation over k, summation over j. When you do this, then I is the only index here, free index. So that means it's a vector, right? So this is a vector. And how do you write this? We write this as omega I, just like a velocity vector. Omega I is the vorticity vector. Okay, and epsilon ijk will tell us the sign, whether it's minus or plus. It can take 1, 0 or minus 1. So we will easily know what is the sign that comes here before your gradient of the velocity field, whether it's minus or plus, very easily. So this is represented like this, and then we have the Laplacian. This you get in a viscous stress tensor term, let's say. The Laplacian also comes when, if you are going to solve the Poisson equation for the pressure. Okay, so this is nabla square u, let's say. This is written as dou by dou xj of dou ui by dou xj. So tensor notations reveals the true form, what it looks like, which differential operator you are going to use in which direction, and yet compact, much better than the vector notations. And with vector notations you cannot proceed in turbulence. We have to proceed only in the tensor notations when we average the equations to get the statistical equations for the statistical motion and equations for the random motion of the fluid. Alright, so we stop here today, and I'll take up any questions if you have.